All right, so now I'm going to get started. And we'll set the camera up so that it looks at the whole board that I will be using. All right, cool. So today, I'm doing things in a little bit of a different order than the book does. So we're on the next section of chapter 10. This is section 4. I'm jumping over section 3 because section 3 is a little easier than section 4. None of these get easy, just easier. But today I wanted to talk about thermodynamics because it takes a minute to get your head around it. The nuclear burning stuff, all I'm going to ask you is to know basically how a PP chain works. And that's easy. It's just P and P, and you get an H, an HE, right? The thermodynamics is a little hairier. Not to say that the nuclear burning is free, but the thermodynamics takes a minute. So, and you're going to have a whole class on thermodynamics. There it is.
That hopefully you'll be teaching because you're the best at it.
Hopefully I will be teaching, but I'm probably not because I'm not on track for that. So I'm probably going to be doing this. But it would be fun. So okay, we're going to start with the first law of thermodynamics. Oh man, that's all. Let's write it. So this I'm going to write up really big. Okay, and we're going to make these little marks. These little marks are funny. They show up on the first day of thermodynamics, and then they go away. Because, here, I'm going to show what I wrote. Actually, I'm going to write it again. So, du. U is internal energy. And this encompasses all of whatever internal energy happens to mean for that gas. So if I have a bucket of hot water, it's the temperature of the water. If I have a block of C4, if I'm going to blow it up, then it also includes the chemical potential of the potential explosion. Okay, so internal energy encompasses all of the internal parts, all of the internal energy. But we're going to deal with ideal gases because we're astrophysicists, and ideal gas works for astrophysics basically all the time. So also it's simple. Since this is the first time we're really getting into anything, we're going to just deal with ideal gases. An ideal gas does not explode. It just is a gas. So internal energy is U. Q is heat flow. So what is heat? Heat is how much internal energy they have, or something. So this is actually how much energy is leaving a system by one means or another. And then W is the work done by the system. Now I can talk about the work done on the system, and then I get a change in the sign on that, but we're not going to talk about that. We're only talking about what the gas itself does. So let's talk about this for a second. So I've got some bottle, some weird shaped bottle. Inside this bottle is some internal energy, U. I got a simple version of what U is for an ideal gas that we'll do later. Oh, I got it. Sorry. Bear with me 1 second. I'm going to... If I rearrange a little bit, then you're not looking through your laptop. Is that better? Mm-hmm. Right. I should have done that like 3 weeks ago, or 4. Okay, so I have a surface. My bottle has a surface. Heat can leave my surface. Heat can leave my bottle. And I draw this with a little hash mark. I'll explain the hash mark in a second. So heat can leave this. What happens if heat leaves my bottle?
It gets cold.
It gets colder. Or
Energy
loses energy.
The energy goes down. That's what you can say. It probably gets colder, but it might not. Sometimes you can leave heat and take heat out. So the energy goes down. Maybe the temperature goes down. We'll see if the temperature goes down later. The other thing that we can do is squish it. So if I take this, okay, now let's draw it like a shape that I can do math with. So now I have a cylinder. Cylinders are nice because it's easy to change just one axis or one dimension. So if I have this cylinder, it has a volume V. If I make it smaller by a little bit, say it's a piston, say I've got a piston and I push the piston in, what happens to the internal energy of the gas? It increases. Why? Because I did.
Work is done on the gas?
Because work is done on the gas. Now, it's negative of work done by the gas. So if I do work on the gas, then the internal energy increases. That's negative work being done by the gas. So that makes that positive as well. So the internal energy in the gas, D, okay, we gotta talk about these D's for a second. D just means tiny little thing. You can make all the dirty jokes you can right now. D is a tiny little thing. This is the little d, okay? So the little d is a tiny little element of something, whatever it happens to be. This is the thing that we're going to take derivatives with. So this is infinitely small. And I mean that in some formal ways, but then we're going to break that. So d means tiny. D, little q. I'm going to call this little q. Now, we have this hash because, okay, what can I do with a tiny little d? Well, I can integrate it. I can add up, what's the integral of d little q?
Q.
Little q. Most of the time, but, so okay, this has got this little hash mark on it, so this isn't true anymore. Because Q as a quantity doesn't really make any sense. Also, the path that I take, so this works, dF equals F works as long as F is path independent. But we need to talk about things that are not path independent. We need to talk about state variables. So what are some state variables? So the state variables for an ideal gas are the pressure, the temperature, the volume, the entropy, which I'll talk about, the internal energy. I think there's some other ones that you can come up with, but I'm not going to, this isn't going to be an exhaustive list. I'm just listing some of the internal state variables. So pressure, temperature, volume, entropy, internal energy. What this means is if I do some stuff to the gas but then bring it back to the same state, then all of these things also go back to the same state. So if I say take a bottle and I squish it and then I bring it back to the original size again, the state variables go back to where they were. Does that make sense? So, for instance, if I think about, have you guys ever had saltwater taffy?
Yeah.
Right. So do you know how to make saltwater taffy? It's a polymer, and you make it by pulling on it. So if I take a block of saltwater taffy, I can measure its resistance, its bulk modulus, which is its resistance to deformation. So if I have a block of saltwater taffy and I poke it, I'm going to feel how squishy it is. If I then work it for a half an hour on the saltwater taffy puller and I poke it again, it's going to be a lot stiffer. That makes sense? That's how taffy works. So the stiffness is not a state variable because I do a bunch of crap and then it's in a different state. But the temperature might be the same and the volume might be the same. So the path that you take to get to a certain state matters, and some of them go back to where they were, and some of them don't. So in something like, say, C4, the chemical composition would not be a state variable because it rapidly changes and you can't change it back. In taffy pulling, the hardness, the stiffness of the bulk modulus is not a state variable because you can't put it back. Q is not a state variable. There isn't a quantity of heat that I can ever have, and there's also similarly not a quantity of work that I can ever have. Right? Also, if I say do a bunch of work on the gas and then add a bunch of heat, I could get to the same thermodynamic state, but not have the same heat flow or work done. So this is a kind of a funny thing that will take a little bit of getting used to, but for the most part, we're going to forget about it. So I can't say the integral of d heat flow is heat flow. That doesn't make any sense. But I can for the rest of the state variables. You can now completely forget all of that because we're not gonna run into anything that really matters. But it's an important bit that always needs to get said. Okay, so du is dq minus dw. What else is dw? So let's talk about dw for a second.
Does DW have the bar on the diesel?
Yes. Work is force times displacement. Right? Now if I multiply this by an area and I divide by an area, then I get this one on the bottom becomes a pressure and this one on the top becomes a volume. This is the cheesiest derivation of this you can possibly find. The book has a much more elaborate derivation, but it's the same basic idea. dW is PdV. This is important. This is so important I'm going to write it over here. Now I'm dropping the little tilde thing because now I stop caring. Because V is a state variable and P is a state variable. So, okay. So what this says is if I've got a bottle of gas and I heat it, I can sort out how much heat flows into it and I can sort out what the state change is. So you did this in 2053 or 2049 where you had, say, a bottle of 15 moles of carbon, let's call it hydrogen because we're astronomers. You have 15 moles of hydrogen at a pressure and a temperature, and then you change the temperature goes up by a factor of 10. What is the new volume? That kind of thing. Do you remember doing problems like that with the ideal gas law?
Yeah.
And then you would also have problems where you had, say, a block of ice. And it starts off at T naught equals minus 5 degrees Celsius. And then you heat it to T naught equals 150 degrees Celsius. So what do? You need to deal with the specific heat of the ice until you get to the phase change. Then you have to worry about the latent heat of the phase change. Then you have to worry about the specific heat of the gas as you expand it. Do you guys remember doing all this?
Yes.
Yes?
Painfully.
Yeah, okay. So this is all the same this is all of that same idea. We're just now doing calculus with it. So what is the internal energy? Let's talk about internal energy of an ideal gas for a second. In the statistical picture of a classical gas, I have a whole bunch of atoms, and each atom has 1/2 kT per degree of freedom. And since I have 3 dimensions, that gives me 3/2 kT for
Is that
every
a measure of energy?
particle. What's that?
Is that a measure of energy?
Yeah, this is the energy. Does that make sense? So here, a degree of freedom. What's a degree of freedom? So this chalk, how many degrees of freedom does this piece of chalk have? Was that? I heard 3 and 0.
4.
It's 4 and 6. Is it 5.
Between negative
No,
infinity
I
and
do.
infinity.
Let's get, okay, all of this,
I'll
so,
say that right.
Wait, 7.
okay,
7?
where can it be? How many ways can this piece of chalk be? Actually, let's try something more
Between
obvious.
0 and infinity.
Let's try this stapler, because it's a little bit more obvious. So, what are the possible parameters? Oh, this stapler has, sorry,
3.
that moves too much. We've got to go back to the chalk. That has too many. Okay, it could be up here, down here, left, right. I got 3 for where it can be. And I got 3, I can rotate it this way. I can rotate it this way. And I can rotate it this way.
9.
6. So I get 6 degrees of freedom. You have 3 spatial degrees of freedom. Now, if this thing was a sphere and totally round and I couldn't tell what orientation it was, then it would only have 3. So a hydrogen atom, a naked hydrogen atom, has 3 degrees of freedom. A carbon monoxide atom has 7 degrees of freedom. No, 5 degrees of freedom, because this one doesn't count. So, the internal energy of an ideal gas is just 3/2 kT, or K over mu mp, because we need to be specific about the specific gas that we have. So, PV equals nRT, that's the ideal gas as you know it. The useful way to write it is PV equals rho T over mu mp. Does that make sense to everybody? If not, let me know. So, the internal energy, I have a formula for this. This is just 3/2 nRT. Or NKT, or KT, sorry. All right. So now, what's the specific heat? Let's talk about specific heat for a second.
Is that MP the mass of a proton?
That is the mass of a proton, that's right. And the specific, and mu is the average mass relative to the mass of a proton. So if I have a bottle of carbon, then mu is going to be 6, because that's the mass relative to the mass of hydrogen. Okay, so heat capacity.
Is the muse reduced or average?
Average mass relative to
It's the average. Oh, this, yes, I'm sorry. Yes, that's important. Mu is the mean molecular mass. Not the reduced mass, not the other mu that we were using. So we use mu in a couple different ways in this class.
So it's not distance modulus here?
It's not distance modulus here.
It's not
More importantly, it's not also the other thing that I'm calling mass, which that one's easy to get confused. Okay, heat capacity. What does heat capacity mean?
How much heat it
How
can
much?
have.
Energy can be contained by mole of gas.
Yeah, so that's a good.
Per degree of Celsius.
Yeah, so several ways to think about it, several ways to write it down. It's something like delta E over delta T. The way I'm going to write it, I'm actually going to write 2. Oh, I'm sorry. I got stuck on something. I forgot to talk about calculus a little bit more. Now I'm going to talk about calculus. I'm not going to talk about heat capacity. Pardon me. I forgot. Let's talk about what things that we like to do with these quantities. So if I have some quantity D, I need a letter.
L.
E.
We don't use,
Which one don't I use?
G.
Z.
Lowercase g.
Y.
H. That's not Planck's constant.
J.
A, B, C, D.
There's just not enough letters.
Wow.
Use 2 letters.
Ooh, now we're talking.
Potato.
I'm gonna use,
Yakuza.
I'm gonna use a little Q
It's
again.
not.
Okay.
It's not, so.
So DQ. Okay, do you guys remember?
D.
State variables. How many state variables are there? I wrote down 1, 2, 3, 4, 5 here. For an ideal gas, there are 3 independent state variables. So once I've defined 3 of these, the other ones I can get. Does that make sense? So there's only 3 independent variables. So that's all I need. So when I'm talking about dq, what is this? Well, it's only going to depend on two other variables. So if my variables are q, r, and s, these are my three independent state variables. If I have something else like chemical processes going on or magnetic fields, there we'll introduce more variables, but we don't have those right now. So little dq, you guys remember chain rule?
Yeah.
Okay, how's chain rule work? df of g of t dt equals what?
Oh, this J rule.
F including g all times the derivative of g.
Yeah.
So df dt, if f is a function of g, which is in turn a function of t, df dt is the partial of f with respect to g times the partial of g with respect to t. Think about it like a fraction. If I have more variables, then this is df dq dq dt. If I have two variables, if f is a function of g and q. Now, I have written the full derivative here, so I also need to write the partial derivative of f with respect to t all by itself, because f can depend on t all by itself, or it can depend on t because it depends on other things that then in turn depend on t. Does that make sense? But this one we're going to ignore for a minute. There's no explicit time dependence on any of these things. If you take hydro with me, next time it gets taught, then we'll have things like that. So, okay, chain rule, let's erase that for a second. The way we like to do this in thermodynamics is dq, this is a full d, is a partial q with respect to r with s constant dr, this is a plain d, not a curly d, plus partial q, partial s, holding r fixed, ds. Right, take a minute with this.
Can you explain the notation
Yes.
of like the bars? What do the
Yeah.
bars do?
So this means I'm holding it constant. So when you first saw this bar when you had integral of df equal from a to b is f evaluated at a, at b and a. Remember seeing it there? This is a similar kind of thing. What it's doing, what this bar says I'm holding s constant. And it's kind of implied by the fact that I'm taking a partial derivative.
Q is
So-
a function of R and S.
Q is a function of r and s. So in this universe, I have three variables. I have q, r, and s, and they're all related to each other by various complicated things. In this way, so q is a function of r and s, r is a function of q and s is a function of q and r. You look confused.
Yeah, so
Okay.
first term, it's the partial derivative of q with respect to r holding s constant times the change in r?
Yeah.
Okay, now I got it.
And the second one is the partial derivative of q with respect to s, holding r constant, times however much r I've got. Yes?
Wouldn't you be holding r constant in the partial derivative of q with respect to s anyways?
In principle, yes. So it's a little bit redundant.
So you don't actually have to write that?
No, not really,
Okay,
but it gets really confusing if you don't.
okay.
So it's a really important bookkeeping thing to know which things you're keeping constant and which things you're not. So, but you're right. So did everybody follow his question? His question is basically, a partial derivative means I'm changing this thing with respect to the thing, holding everything else constant. That's kind of what a partial derivative means. So I fix everything else. When we're doing thermo, we'd be a little bit explicit because if you don't, then you're gonna throw out the wrong thing. So it makes life a little easier. I'm actually gonna write this over here too, just so we remember it. Now, okay, this is a hard D, this is a total little differential of Q. It's the partial of Q with respect to R, holding S constant, times d R. So the R here goes with the R here. It's gotta cancel out, in a way. Plus partial Q, partial S, holding R constant, ds. So now, we like to, I want to, but I'm not going to go down the deep rabbit hole of writing this down for all of the state variables and watching how all of the various derivative terms get related to each other. There's a whole class on all of these relationships. So I can look at the partial of heat flow with respect to temperature holding pressure constant. I can think about the partial of energy with respect to temperature holding volume constant. I can think about the partial of entropy with respect to temperature holding energy constant. I can think about these things, and then I can relate them together. There's machinery that you develop that lets you relate these things together, which we're not going to really build here. Good. Does this make sense to everybody? This chain rule business and how I'm going to use it? So we use it a little bit. I'm not going to really exploit this, but basically all of thermodynamics is just exploiting relationships like this. Okay. That's it for math. So now, I can write this down, and there I actually have to stop. So CV I'm going to define as partial Q, partial T holding volume constant. We'll take this as the definition right now. You might like a different definition better. It's related through these partial derivative relationships that you'll develop in thermo.
And what is CV?
CV is the specific heat at constant volume. The specific heat at constant volume. And then we can also define CP is dQ dt, and here I mean actual Q, big Q heat flow at constant P. So this means that if I change the temperature of the object, how much heat has to come out? Or if I take out so much heat, how much does the temperature change? If I hold the volume constant, or if I hold the pressure constant. Does that make sense? Is everybody all right there?
Yeah.
With those? So, let's look at what CV is. dQ dt, oh, let's change this. dQ dt at constant V, well, I just look up here, and I have that dQ equals du plus P dV. So dQ dt at constant V dQ is du. So this is just du dt at constant V. What's du dt at constant V? I wrote it down. Let's write it down to get a little more explicit. U equals 3/2 K over mu MP T. So what is the derivative of U with respect to T? Sorry. Let me keep it with, I'm going to do this keeping it consistent with the book. I don't like R, because I don't like moles. It's a dumb arbitrary unit. I like actual numbers, so I like using K because I don't ever have to measure a volume of things, so I don't care. So U is 3/2 nRT. So what is du dt? It's just 3/2 nR. Does everybody see that? So this is just 3/2 nR. So CV is dQ dt at constant volume, which is just du dt at constant volume, which is 3/2 nR. So CV, I'm going to write this over here. or 3/2 K over mu MP. So if I want to change the temperature of something, I'm going to change the internal energy based on CV. And CV is just based on the molecular weight of the gas, really. So let us sort out the other one, CP. Where are the notes that I like? This is one derivation that if I try to do it cold, I mess it up. Not really that bad, but okay. Sorry. First, I got to talk about entropy. Sorry about that. CP. We'll talk about CP in a second. No, I'm sorry. It's the wrong page of notes. Getting ahead of myself. We don't need to talk about entropy yet. I'm talking about CP. Yeah, okay, so dq dt at constant volume is CV. dq dt, so the heat flow change with respect to temperature change at constant pressure is CP. du, I'm going to write du is dq dt at constant pressure, P, dt, sorry, minus P partial V partial T at constant P, dt. So you know how I just showed you this partial derivative thing? This is the same idea, so how do we get here? So we get here by saying du equals du, sorry, du, that's a hard D, is du dt at constant pressure, dt, plus du dv at constant temperature, dv. So we do something like this, and then we do stuff that you learn in thermo. You can see the first term, the second term's a little harder to see. But we're left with this term here. So this quantity here is just CP. And this quantity here, we'll sort out what this is. And du, I know that du is CV dt equals all this stuff. So now we need to go play around with this, with what this thing is. So P partial V partial T. We got to sort out what that is. So PV equals nRT. So now I'm going to take a derivative of this with respect to nothing. So I'm left with, so I'm going to do D of all of these things.
So disrespectful.
Was that?
So disrespectful.
To take it with respect to nothing?
Yeah.
That's actually right. Sorry, I had to say it all the way out loud before I got weird. Okay. So I'm going to differentiate this. What's dPV? This is chain rule again, or the product rule. The product rule is chain rule. dPV is P dV plus V dP. Does that make sense?
Oh yeah, I just considered it. Yeah.
Why I can say that? So this is a tiny little element of V times P. It's P times a tiny little bit of V plus V times a tiny little bit of P. Sometimes I hate sentences. And then the other side is, let's see, how did we write this? Yeah. RT dN plus NR dt. So R is a constant, but the chemical composition is not. N is the chemical composition here. Or the number density, or it's the N in NRT.
So much happening.
Was that?
So much happening.
Oh yeah, we haven't even really gotten started yet. So
Okay, what is CP?
CP is the specific heat at constant pressure.
Okay.
So let's back up there. I'll just do it again. If I say it again while I'm writing, if you didn't understand what was written there, then it's okay if I erase it. I'll say it again and we'll talk about it again. So, okay, so CV is the specific heat at constant volume. So what this means is I have a bottle, I light a fire under it, heat goes in, temperature goes up. CV gives you the relationship between dQ and dt if I keep the volume constant. So it's how much heat I need to increase the temperature by a certain amount,
Okay.
keeping the volume constant.
Yeah.
Does that make sense?
Yeah, I've
So
seen
now
that
this
before.
is like a rigid bottle. This is like a steel bottle.
Steel.
Or a glass bottle, but that can break a little bit. Constant pressure. If I have a balloon, little kid, look at his balloon. A balloon's going to be basically constant pressure because if I increase the pressure of the room, the balloon will squish, right? So if I add heat to the balloon, then the balloon will expand and the temperature will go up. But at constant pressure, how much heat do I need to increase the temperature of that gas? So CV is change of heat keeping the volume constant. And CP is change of heat keeping the pressure constant. And we're going to need both of these things. Because what we're going to do, where are we going? Let's talk about where we're going. What we want to do I have this hot thing at the bottom of my star. And then I have stuff in my star. I want to know, how is the heat getting out? Is it going to get out through conduction? Is it going to get out by convection? Or is it going to get out by radiation? That's really where we're going. We're going at getting criteria for when conduction or convection happens.
So,
I'll give you a hint, conduction never happens. The question is whether it's convective or radiative, whether or not this is just a very bright flashlight lighting the whole thing up, or whether it's hot enough to start the thing to boil. So that's where we're going. So we need to know how much heat a little blob of gas can take before it changes. So we need to know what CP and CV are. Does that make sense? Did you have a question?
I think I got it.
All right.
The hot stuff is that stuff, or is it just hot without stuff?
There's stuff too.
There's stuff.
Yeah.
Okay.
So it's all hydrogen.
Okay.
So it's all made out of hydrogen, but at the bottom it's very hot, and then the nuclear burning is located at the center.
So I
and then
mean, if
heat
you're
has to get
doing
afterwards.
convection, would
Uh-huh.
this hot stuff move into the stuff?
No.
No.
The burning stuff stays at the bottom. You don't typically get convection that goes down into the burning material. And if it did, it would stop burning,
Okay, because then it's too hot.
because then it's not dense enough or hot enough. But we don't need to worry about that. So we've got a core that's burning, and this is hot. We'll just pretend it's hard right now. And then we'll get convection plumes that rise up out of that. Did you have a question? Is there a question over there? I thought I saw a hand. Oh, you did.
What's little q again?
Little q was my dummy variable that I was just horsing around with.
Oh.
So you don't need to worry about little q. Little q stands for everything.
Also, why is there a bar on DQ?
On that dq?
Yeah.
So q isn't a state variable, and the real difference, the bar indicates things that aren't state variables. So that isn't a property that the fluid has, it's something that it does. And since it's that way, you can't get it back. I can get the volume back to where it used to be, but I can't get the heat back once it's gone. Does that make sense? Don't worry too much about the little bars. You'll see them again when you get to
You
thermal.
said the little bars are on things that are not state variables?
Yes. All right, so we want to sort out what CV is. So CV is how much heat can my ball of gas take if I keep the volume constant. And that's easy. That's straightforward. You just say du is CV dt. CV is just the stuff here, 3/2 nRT. CP is a little bit more complicated, and they're related, and we need them both because we got to get to this other relationship. And we're not going to use the funny thing is I develop these things, but we don't use them a ton. What we use is a thing that we derive out of these things. Okay, so CP is partial heat flow, is the change in heat flow with respect to temperature, holding pressure fixed. So this is like a balloon. So how do we get to that? So what we can say is du is partial Q partial T at constant P dt. So this is, think about this like a slope and a line. So this is like the slope of the line, and this is, maybe don't think about it that way. Maybe don't think you're there yet.
Just don't.
Minus P dV dt at constant pressure dt. So this is a similar kind of thing that I wrote before. So we like to write things like dq equals partial Q partial A holding B fixed dA plus partial Q partial B holding A fixed dB. So this is just chain rule. That's all it says. This is chain rule plus a little bit of thermodynamics that I'm skipping that you can kind of see, and it doesn't take you all that long, but I'm not going through it. But this equation is another statement about what a tiny little element of internal energy is. It is a tiny little bit of heat flow at a constant pressure times the temperature change, plus a tiny little bit of squishing, so this is a little bit of work at constant pressure. So now we need to sort out what all these things are. So this thing is, I know what this is. I know what du is. du is CV dt. Chalk is now too small to use. Let's use this one. And this is equal to Cp. This thing here is Cp dt. That's because this is Cp minus P partial V partial T holding P fixed dt. Okay, this is kind of horrible. Let's get at what this is. What is partial V partial T? Change in volume with change in temperature. Let's get it, because we know the ideal gas law. So PV equals nRT. I'm going to take a derivative of this, and I'm left with dP, V dP plus P dV equals nR dt plus RT dN. So this is the ugliest thing that I've written so far. Maybe it's not.
Pretty bad.
It's pretty ugly.
It's all pretty bad.
So all I've done is this is just product rule on this thing, okay? Remember product rule? Right, this is just product rule twice. So it's PV turns into VDP plus PDV. And nRT, R is a constant, it's like 8.3. N is not and T is not, so you get nRDT plus RTDN. So all I'm doing is I'm saying, what are the things that can change? This thing can change, this thing can change, this thing can change, and this thing can change. So when I want to say how does it change, I have to have a little bit of change for everything that I can. I mean, it's just an accounting issue. So now, we're saying that N is constant because it's not exploding and it's not settling out, it's not freezing. And we've already said that P is constant. So these things being constant means that the D of that thing is 0. Does that make sense? So how do I use these two pieces of information to make this equation less ugly? Cancel what?
Cancel them out.
Cancel which out?
VDT,
And RTDN.
Oops, not that one.
Yeah.
I want that one. My aim was off. So the VDP I can kill, because P is constant. And the TDN I can kill, because N is constant. And I'm just left with P dV equals NR dt. Or P dV dt equals NR. Does that make sense? I haven't done anything fancy, it's just a little bit of calculus. That doesn't mean it's easy, it's just, I haven't done anything that you shouldn't, that you can't follow. So we plug that into here. We'll clean up a little bit of our mess. So I take this equation and I've got CV dt equals CP dt minus NR dt, or CV plus equals, sorry, let's write it the way it's always written. CV plus NR equals CP. So this is a relationship that you need. So what this says is that the amount of heat it takes to heat something up at a constant volume is the amount of heat it takes to heat something up at a constant pressure plus all the extra heat that you need to do the work, NR. Okay, so I've gotten here. Now, I wanted to go through the process because the process is very similar to
It's equal to CP, right?
CP,
You wrote
thank
CP, so I'll just, which one's?
P on the right side. Okay, we haven't gotten to the part that I care about yet. We're just building up some machines that I need to use to get to the part that I care about. Don't worry, it's a
These are
lot
some
further away.
Ugly fucking machines.
Oh yeah. Oh, you have no idea. No, they're so beautiful once you get used to them. Like it's like those stereograms. Did you do those stereogram things that are like a field of dots that you gotta stare at? And
So
cross
you
your
have
eyes a little bit?
Stockholm syndrome.
Oh, it's worse than Stockholm syndrome. Stockholm syndrome.
It's not just holding you hostage, it's also beating you daily, is that what the difference is?
It's deeper.
The beatings will continue until
Oh, shit.
morale improves.
Physically and psychologically?
Yeah. Speaking of, it's 1:15 and I've gone over by 5 minutes, so it's time to stop. Okay, this is where I'm gonna pick up on Friday. Is there a reading on Friday?
Yeah.
You said there's one every day.
I said there's one every day.
Here, I can
You
check
should
right
move it.
now.
It's 13.1, 13.2.
13.1, 13.2. Okay,
Yeah, I mean, we're behind on readings class-wise, aren't we?
Not by a lot, but
by a lot.
but if I don't change the readings, so okay, don't do the reading for Friday.
Okay.
Okay.
Sounds good.
It'll come up next week.
Okay, well, I'm behind on readings anyways, so.
It's okay.
I'm sorry, this week has been hectic.